today we're going to present sample size considerations in pharmacoepidemiology studies. In planning pharmacoepidemiology studies, one important thing is to consider the sample size, and we have to determine it from the perspective of one who is designing a study unit. For the study designs, in the cohort studies, subjects are selected based on the absence or presence of the exposure, and it will be followed to determine whether the disease of interest will be developed or not in each. However, in the case control series, subjects are selected based on the absence or presence of the outcome, and investigators are interested in the prevalence of the exposure in each. And finally, for the case series, they are descriptive studies used to generate a hypothesis and not to test them. They describe the clinical experience of many patients with a particular drug. To calculate the sample size for a cohort study design, one should first start by specifying 5 variables: alpha or type 1 error, beta or type 2 error, the minimum effect size, the incidence of the outcome of interest in the control group, and finally, the ratio of unexposed controls to exposed subjects. Type 1 error is defined as the probability of concluding that there is a difference between the two compared groups when in fact a difference does not exist. Alpha will be set to 0.05 conventionally, and the greater the tolerance for type 1 error, the smaller the sample size required, and vice versa. Alpha can be either one-tailed or two-tailed. It is said to be one-tailed whenever one of the study groups is more likely to develop the disease, and investigators are interested in detecting this result only. However, it is said to be two-tailed if either of the study groups is likely to develop the disease and investigators are interested in either result. Type 2 error is defined as the probability of concluding there is no difference between the groups when in fact a difference does exist. The complement of beta is the power of the study, and beta is conventionally said to be 0.1 or 0.2. The greater the tolerance for a type 2 error in a study, the smaller the sample size required. And unlike alpha, beta is always one-tailed. The minimum effect size is expressed as a relative risk, and the smaller the relative risk, the larger the sample size required. Incidence of outcome of interest in the unexposed control group. The rarer the outcome. Let's see this example. In a study including 2,319 exposed individuals with an equal number of controls, the power achieved will be 0.8. However, increasing the size of the controls even further, as you can see in this table, will result in progressively smaller gains in statistical power. Once the 5 variables have been specified, we can use this formula to calculate the sample size needed for a cohort study design, where P will be the incidence of the outcome or the disease in the control group. Let's say one wanted to investigate a new anti-inflammatory drug about to be marketed, but pre-marketing data raised the possibility of hepatotoxicity. Then one would use a cohort study design to answer such a research question. And the sample size would definitely differ depending on the 5 values that are chosen for the 5 variables that were discussed previously. Assuming hepatitis is the outcome and it occurs in 0.1% of the unexposed individuals, and we want to detect a relative risk of 2 for this outcome, alpha is said to be 0.05 with a beta of 0.1. This would require a total of 31,483 subjects. Now, if one were less concerned in missing a real finding, even if it was there, then beta will be increased from 0.1 to 0.2, and this will result in a reduction in the sample size to be 23,518 subjects. Now, let's say we want to limit the number of exposed subjects, and we can include up to 4 controls for every exposed subject. This would result in a sample size of 13,402 with 4 times as many controls. Finally, in contrast, if the goal of the study was to investigate a much more common outcome, unlike hepatitis, let's say it was abnormal liver function tests, which occurs in 1% of the unexposed population, and we want to detect the same relative risk of 2 with the same alpha and beta. Now, this time, only 3,104 subjects will be needed, which is a much smaller sample size.
The approach to calculating the sample size for a case-controlled study is going to be similar to that in a cohort study. Again, 5 variables need to be identified: the alpha or the type 1 error, beta or type 2 error, the minimum effect size, the odds ratio in this case, the prevalence of the exposure in the undiseased control control group, and the ratio of the undiseased controls to diseased study subjects. Now, in case control, we are interested in the number of the undiseased control and diseased subjects. The principles in deciding upon the appropriate ratio is again similar in both study designs, and usually here also there is rarely a reason to include a ratio greater than 3:1 or 4:1. The formula for calculating the sample size for a case-controlled study is similar to that for a cohort study, and here the P is the prevalence of the exposure in the control group. Now, what if one wanted to investigate the use of an unsafe drug that's about to be marketed, but pre-marketing data raised questions about hepatotoxicity? So the sample size definitely is going to vary based upon the values chosen for the 5 variables, and assuming that we want to detect an odds ratio of 2, with an alpha 2-tailed 0.05 and a beta 0.1, and assuming that the drug is commonly used, such as ibuprofen, 1% used by the population, then the sample size required will be 3,210 and of the diseased subjects, and also an equal number of the undiseased controls. Now, if one were less concerned in missing a real association, even if it exists, the beta can be increased from 0.1 to 0.2, and therefore the sample size will be decreased to 2,000.
So in case series are used in pharmacoepidemiology to quantitate better the incidence of a particular disease in patients exposed to a newly marketed drug, used to predetermine whether the disease occurs more frequently than some predetermined incidence in exposed patients. Most often, the predetermined incidence of interest is 0, and one is looking for any occurrence of extremely rare illness. So to establish drug safety, a study must include a sufficient number of subjects to detect an elevated incidence of a disease if it exists. First, we need to calculate the incidence rate from the study's results, which is calculated as the number of subjects who develop the disease of interest during the specified time interval over the total number of individuals in the population at risk. For example, if 3 cases of a liver disease are observed in a population of 1,000 patients exposed to an NSAID during a specified period of time, the incidence will be 0.003. In this example, the lower limit boundary of the 95% confidence interval is the corresponding lower limit factor multiplied by the incidence rate, and the upper boundary of the 95% confidence interval will be the corresponding upper limit factor U multiplied by the incidence rate. Thus, the incidence rate is 30 per 10,000, and there is 95% chance that it lies somewhere between 6.18 per 10,000 and 87.6 per 10,000. Now we're going to be talking about the rule of threes, which is a simple guide useful in situations. Now we're going to be tackling the missing variable. In the above discussions about the sample size calculations in cohort and case control designs, we assume that one is able to obtain info on each of the 5 variables that factor into the sample size calculation. Is that in fact realistic? 4 of the 5 variables are totally in the control of the investigator, subject to his specifications, which are the alpha, the beta, the ratio of control to study subjects, and the minimum effect size. However, only one of the 5 variables is derived from other sources. In cohort studies, it is the expected incidence of disease in the control group, and in case control, it is the expected prevalence of the exposure in the control group. The missing variable can be approximately estimated by the existing data source, which is the vital statistics or commercial drug utilization, the medical literature, such as research for studies that have collected these data for a defined population, and thus assume our population is similar, and conduct a simple pilot study within the population, or just guess.
As for studying multiple outcome exposure variables, the investigator will base the study sample size on variables that lead to the largest requirements. Thus, it will provide more power for the outcome and exposure, and will permit subgroup analysis. As for limitations, previous discussions focused on dichotomous variables, and the information on sample size calculation for continuous variables weren't discussed, such as serum cholesterol, blood pressure, height, weight. Although the use of continuous variables results in a marked increase in the study power, epidemiologic studies do not have the luxury of using such variables. An unusual problem encountered in our studies is having a too large sample size. One can find statistically significant differences that are clinically trivial, and sudden findings, even if statistically and clinically important, could have been easily created by biases or confounders. Thus, this should not be ignored but interpreted with caution.